Hi, my name is Trent Greer, and this is my presentation on extracting device fingerprints from flash memory by exploiting physical variations. As mentioned in the title of the paper, we are going to be looking at exploiting physical variations in flash memory. Flash memory is widely used in modern devices, making it feasible and accessible for use in computational research and applications. Flash memory has some problems such as unpredictable access latencies and reliability that arise from manufacturing variations and that can be detected through a device's electronic interference. This can be potentially beneficial. Manufacturing variations and issues generate a sort of randomness, which can be applied to a wide range of use cases. Now let's look at the concept of physically unclonable functions, or PUFs. Physically unclonable functions rely on a physical object that takes in an input and produces a unique digital signature or identifier as its output. Therefore, physically unclonable functions can be used for things such as generating unique keys or for integrated circuit authentication. So we can actually utilize flash memory to create physically unclonable functions, referred to as flash-based physically unclonable functions, or FPUFs. As stated earlier, flash memory is used in most modern devices and would therefore be relatively easy to implement in existing devices with flash chips, and a manufacturer would have no need to create custom circuits or hardware for new products. This process also relies on the already existing variations in manufacturing flash memory. We can utilize flash-based physically unclonable functions for a number of things, such as device counterfeit detection, device identification, and random number generation. For an example with device authentication, we can assume a server has a copy of the flash signature of all legitimate devices allowed access. Therefore, assuming the server has not otherwise been compromised, a legitimate device trying to access said server can send its flash chip signature in order to be authenticated, while a malicious device cannot. Finally, flash-based physical unclonable functions rely on the probabilistic outcomes of manufacturing variations and differences from operation to operation. Therefore, in-device behavior can be used to create a random number generator. In order to implement flash-based physically unclonable functions, we need to first understand the concept of flash cells, array organization in flash chips, and variation mechanisms in flash chips. Flash memory consists of flash cells, which are signal floating gate transistors and store at least one bit. A flash cell, as depicted in the slide, is typically arranged in groups of between 32 and 64 in an NAND flash chain. Charge on the floating gate affects the threshold voltage of the flash cell, so by turning on all transistors in a flash chain except the target can be read. A chip can measure its own threshold voltage by applying a voltage to the control gate and measuring flow through the target cell. Flash memory then allows for programming, reading, and erase operations on individual cells. Flash chains, composed of flash cells, are then organized by the thousands into a memory array that supports reading, writing, and programming sizable amounts of flash cells at the same time. A block is the basic unit in a flash array and is made up of between 16 to 32,000 parallel flash chains. Individual cells in a chain all comprise a different page. For example, each first cell in a chain is part of the first page in a block, the second cell in a chain is part of the second cell in a block, and so on. In a page, all the gates on all transistors are connected by one word line. Programming and reading operations apply to separate pages, but erase operations will erase an entire block. There are thousands of blocks in each flash chip. Because of the structure of a flash chip, two bits in different pages can influence each other. When a read or program operation occurs, word lines experience an intermediate gate voltage, which allows the current to flow to a target cell. This causes electromagnetic stress on the oxide layer of every bit. After this happens multiple times, the collective electromagnetic stress could create bit errors. In order to maximize density, flash cells are packed as tightly together as possible. Therefore, small differences in cell shape and size, as well as oxide thickness on transistors, can measurably impact individual cell behavior and intercell effects, such as capacitive coupling between cells. This impacts how likely it is for read and program operations to cause disturbances or for program and erase operations to induce wear. This also can create more difficulty in programming and erasing blocks as both program and erase operations are iterative and can therefore cause latency between pages and blocks. These physical effects can be considered random due to their unpredictable electronic nature, and we can safely claim that the pattern of variation between chips, blocks, and pages is uncorrelated. This makes flash chips great for physically unclonable functions, as consistency should be unreliable across flash devices. Signatures from flash devices were extracted via a testing board with two flash chip test sockets connected to an XUP board running Linux. A flash controller running on the field programmable gate array was custom built to help researchers access flash memory. This also allowed for the sending of erase, program, and read operations. And the XUP board contains a custom flash controller that creates timing measurements with 10 nanosecond resolution. Here are the parameters for the 27 flash devices that were used as a part of this study. As noted, the flash devices had variations in manufacturer, page size, and the number of pages per block. The chip's varied geometry accounts for the electromagnetic effects and problems previously mentioned in this presentation. This makes evaluation of a flash-based physically unclonable function both easier and more meaningful. So, what should be our criteria for what constitutes a useful flash-based physically unclonable function? First, it should be fast. In every use case given, we rely on quickness. A manufacturer loses money spending time verifying thousands of flash chips. A server cannot function well with slow authentication times. Cryptographic functionality depends on being able to produce many large random numbers at a time. Secondly, it should not cause significant damage to the flash device. This is bad for the end user in any scenario as it limits the lifespan of their device significantly. Third, there needs to be a low false positive rate, meaning that two flash chips should hardly ever produce the same signature, or else we will lose the uniqueness of any identifier and can reproduce cryptographic functionality. Finally, it should be hard to counterfeit signatures in order to decrease the likelihood of malicious actors exploiting our system. In order to calculate correlation for the sake of identifying if a method will produce false positives, we'll use the formal correlation metric known as the Pearson correlation. For two different signatures, we take each bit in the same position. Bits from one signature will be denoted as X, and bits from another signature will be denoted as Y. We then form the pair XY for each bit in each position, and then calculate the correlation from the formula shown. The closer the result is to 1, the more similar the signatures are to each other. Conversely, the closer the result is to 0, the more the signatures are dissimilar. First, in order to measure counterfeiting feasibility, we must quantize signatures and measure their correlation with the original. We can then measure the entropy of the quantized signature using the formula given on the slide. P sub I is the probability that a bit had the value I in the quantized signature. If the resulting entropy is close to 2, then created signatures are not significantly compressible, suggesting they couldn't be stored on the flash chip and are thus less susceptible to counterfeiting. If the resulting entropy is not close to 2, then created signatures are significantly compressible and more susceptible to counterfeiting. The first flash-based physically unclonable function we will take a look at takes advantage of the program disturb variation. As shown in the algorithm, a signature is created by erasing a single block and then programming one page in said block over and over. After each program operation, adjacent pages are probed for program disturbed induced errors. We then take note of what bit caused an error and place it into its corresponding place in our unique signature. If a bit is never affected by the program disturb, the corresponding value for that bit is set to 0. Otherwise, it is set to 1 in the complete signature. As shown in the figure on the left, creating signatures from the same page multiple times creates highly correlated signatures. However, as shown in the figure on the right, creating signatures from two different pages is noisy and generally uncorrelated. This means creating two signatures on the same device creates the possibility of the signatures sharing many characteristics, but two signatures created on different devices will not. For most of the use cases stated previously in this presentation, such as identifying counterfeit devices and device authentication, this is acceptable. However, if one needs to use a random number generator, this would not be acceptable due to high correlation between numbers created on the same device. This chart further expands on these correlations by testing with a larger number of devices. The white bars represent the correlation of signatures from the same page, while the black bars represent the correlation of signatures from different pages. This confirms the results that were previously stated. This means that the program-disturbed flash-based physically unclonable function fits the criteria of having a low false positive rate. However, we still need to look at the other aspects of this method. It takes about 1 to 5 minutes to produce a signature when using the program-disturb based method due to the need to run thousands of program operations to disturb a single bit. In order to reduce this latency, we must sacrifice some of the signature's variability by limiting the number of program operations used to produce a signature. Let the variable k be the number of programs used to create a signature. The figure shown on the slide shows the effects of changing k on the variability between signatures from both the same flash chip and signatures from different flash chips. The lines each represent a different signature from a subset of the hardware being tested on. The solid lines represent variability in signatures created from different pages, while the dotted lines represent signatures created from the same page. We can clearly see that using more than 5,000 programs lets us distinguish between signatures reliably, but using less than 4,500 programs does not give us enough variability to distinguish between these signatures. Having signatures created from 5,000 programs takes around 50 seconds. This is a relatively good time, but perhaps not quick enough for time-sensitive applications and may be a drain on resources for use cases that require great performance. Creating counterfeit signatures from the ones produced off this base method would not be impossible. Obtaining a program-disturbed signatures follows an easy-to-detect access pattern due to the signature's creation's unusual nature. The malicious actor would have to store the signature information inside the flash chip, be alerted to attempts to retrieve the signature, and finally replay the signature back on said attempts to retrieve the signature. However, the manufacturer of the device has options to prevent this. The signature can instead be created from a subset of random pages, which would force the malicious actor to store the signature information for every single page. Researchers found that the created signatures are not significantly compressible, meaning forging signatures from this method after the manufacturer adjustments would then not be realistic for a malicious actor. The second flash-based physically unclonable function we will take a look at is the read-disturb method, which follows a similar programming pattern as program-disturb. First, we erase an entire block and then reprogram it with a random bit. Then, each page in said block is read millions of times over to induce read-disturb. Each page in the block is checked for errors after every 1,000 read iterations. If an error is found, the bit, page, and cycle of the error is recorded. The read cycle counts are what make up our final signature. The process is repeated 10 million times to ensure the creation of a unique signature. Read-disturbed signatures follow a similar pattern of correlation to program-disturbed signatures, but with more extremes. Correlation of read-disturbed signatures from the same block was even greater than the correlation of program-disturbed signatures from the same page. However, correlations of read-disturbed signatures from different blocks were extremely low and much better than its program-disturbed signature counterpart. Again, this is potentially great for counterfeit detection and device authentication. Read-disturbed signatures are also safe on the underlying hardware and do not cause significant damage to the device over time. This is because the read operation does not move the charge of the floating gate. However, creating read-disturbed signatures is incredibly slow, especially when compared to our program-disturbed method. Creating a useful signature from certain chips takes around 6 hours, and some chips are less susceptible to read-disturb errors to the point where creating a signature wasn't even possible. This is completely unacceptable and unreliable when it comes to any legitimate application. Furthermore, it is easy to counterfeit signatures created with read-disturb. Quantizing the signatures to 1 bit gives correlations above 0.98. Signatures created only disturb 3 to 7 bits in 6 hours, so it would be possible to store all of the forged chip signatures on a single chip. Now we will look at two flash-based physically unclonable functions that both use bit-level variations in program latency to create a signature. Both functions program a single bit at a time in a page and use the latency of the operation to create a signature. For creating both single-page and multi-page write latency signatures, an entire block is first erased. Then the single page variation programs a single 0 followed by ones in the first page of the block. It then programs 2 zeros followed by ones in the second page of the block. This pattern is repeated for all pages in the block. Conversely, the multi-page variations only programs the nth bit on page n, ensuring the program operations are spread throughout the block. After n program operations, the entire block is erased to ensure that each program operation is performed on an erased page. For both variations, each flash cell contributes one part to the string latency values which make up our final signature. Both SLC and MLC chips have similar selectivity otherwise generally. Signatures from the same page show a correlation around 0.83 for both, and signatures from different pages show a correlation around 0.02. This difference isn't as profound as the program disturb and read disturb based signatures, but it is still a large enough difference for it to be significant. The graphs shown both measure single page write latency selectivity. The left graph looks at SLC devices where 100-bit program latency measurements have correlations over 0.8 and provide good selectivity. The right graph looks at MLC devices, but we find that 100-bit program latency actually decreases selectivity as the number of bits rises. This is because of the flash chip's memory array architecture as previously described and means we should still stick to smaller signatures when using program operation latency functions. Smaller signature sizes can create some issues for write latency signatures. As a general rule, it is easier to forge smaller signatures, and we cannot increase the signature size without affecting our selectivity. However, write latency signature generation is significantly faster than previously discussed methods. It only takes about 2 seconds to create a usable signature, and said signature can be extracted quickly as well in one operation. This also comes with almost no damage to the underlying hardware due to the speed of the method and the specifics of the write operation. There were some other potential sources for signatures examined, but all turned out to be unviable. Erase latency signatures measures the erase latency for a block and creates a signature similar to how this process is used to create signatures from write latencies. However, latency times didn't differ from each other enough to make a proper unique signature. Read latency signature again uses the same idea as write latency signatures, but the read operation latency is consistent or even constant across multiple devices, meaning it would create similar or the same signatures and run into aforementioned problems about making signatures unique. Whole page program latency signatures also suffer from lack of difference in latency times and was thus also ineffective. Finally, program/erased where signatures observe the wear caused by the program and erase operations and try to derive signatures from that. However, this is ineffective for two reasons. The first being that inducing sizable enough physical wear to produce a unique signature would take multiple hours and heavily damage the device, which is bad for the end consumer and the manufacturer. The second being that a malicious actor could easily observe what part of the device was worn down and reproduce the signatures that way. Here is a table summarizing the results of the research. As discussed, multi-page bit program latency, single-page bit program latency, and program disturbed flash-based physically unclonable functions can be used to create viable, unique signatures that satisfy the use cases discussed at the beginning of this presentation. This makes them great choices for a wide variety of applications, along with their speed and created sizes. We can also see that read disturb could create a unique signature, but it is unfeasible due to the extremely slow speed of the method. We can also see why the unviable methods are unviable. In conclusion, this presentation suggested Flash-based physical unclonable function use cases and use case scenarios such as device identification, counterfeit prevention, and random number generation. Hardware manufacturers can use their already existing devices to allow for device authentication and cryptographic uses. In addition, this presentation outlined the criteria for a good Flash-based physical unclonable function, which includes signature generation speed, little to no physical damage to the hardware, low false positive rates, and having signatures be hard to counterfeit. This makes it easier for researchers to look at new Flash-based physical unclonable functions and to evaluate their usefulness. Finally, this presentation showed reliable and viable Flash-based physical unclonable functions and the methods for creating and implementing them. This means Flash-based physical unclonable functions are already available for use and implementation.